Before we can discuss methodology, application, and various platforms which can be utilized to achieve such, we need to discuss the fundamentals. And some of the most fundamental topics as it pertains to the field of statistics are standard deviation, mean, median, and mode. And it's important that you understand these various concepts as we move forward because much of the field of statistics is built upon these topics in one way or another. So let's begin this lecture, and I appreciate you coming and spending time here, and we'll get started. So probably the most basic of the concepts, which we'll be covering in this particular video, is mean. And you've probably encountered mean at some point or another in your daily life. Mean is synonymous with average. So if anyone ever asked you to average a series of numbers or, hey, what's the average? What they're referring to, at least scientifically speaking, is the mean. And the mean serves to summarize a given group of data, often to better understand the overall value of a given data set. Now, similar to the concept of mean is median, and some of you may have encountered this. More, I would probably assume have not. However, in statistics and probability theory, the median is the value separating the higher half from the lower half of a data sample or population or probability distribution. And really what this entails is, in layman's terms, is it's the middle value in a series. So when you think of median, think of middle. You know, you're driving the car and you have to watch out for the median. Think of middle as being synonymous with median. And we'll get into this in a moment with an example, but first we're going to talk a bit more about mean. So let's derive the mean. We have our sample series, which is comprised of these various elements. And to find the mean from this particular series, we just have to add those numbers together. All right, so as you can see, we're adding 2 plus 8 plus 6 plus 1 plus 4, and so on and so forth. And once we achieve the sum of that series is 54. We now need to discern the size of the series. And the size of the series is the number of observations within it. So in this case, n is the number of observations in our series, and n equals 10 because there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements or 10 numbers or 10 observations within our series. So how many numbers are we summing to get the mean? Well, 10. So the size of our series is 10. So then we just divide the sum of the series, which was 54, by the size of the series, which was 10, and we get the mean value, or the average, which is 5.4. So what is the mean of this sample series? It's 5.4. So try this at home if you like. Now, as I discussed in a prior slide, the median can be remembered as being the center point or the midpoint of a data series. So what we need to do to derive the median is we have our series, our sample series. First thing is first, we need to reorganize the series in ascending order. So that means take the lowest numbers and list them first up to the highest numbers. So our lowest number in this series is 1, so we start with 1, and then we have 3, and then 3, and then 4, and then so on and so forth until we have that particular step achieved. Then we discern the size of the series. So how many numbers are we working with? We're working with 9 in this case. And then we need to find the value which represents the midpoint of the data series. All right, so let's see what we mean by this. So we have 9 observations, 9 numbers in our series. So the middle number, if we're counting 1 to 9, is the number 5. So let's count. 1, 2, 3, 4, 5. Middle number right here. 6, 7, 8, 9. So our median is 6. And let's do this again. All right. We have 9 values. 1, 2, 3, 4, 5. There's our midpoint. 6, 7, 8, 9. And it's simple as that. So what is our median value? It's 6. Now you're probably thinking, all right, well, it's easy enough when you have an odd number of observations. What if we have an even number of observations? Well, I'll show you how to work through an example of that scenario in this slide. So again, we have our data, our sample series. For any of this work to work, we always have to reorganize the series in ascending order. So smallest value to largest value. So smallest value is 2, all the numbers in between in order. Largest value is 7, there it is. There are 10 numbers that we're working with, 10 observations, or 10 elements within our series. So lowercase n equals 10. So as you can see, 10 is a even number. It's not going to be easy for us like it was with our last example where we had an odd number of observations. In this case, we have 10, which is an even number. So we still need to find the value which represents the midpoint of the data series. So let's do the count first. 1, 2, 3, 4, middle value, up 2 middle values in this case. 1, 2, 3, 4, middle value, 1, 2, 3, 4. Or 1, 2, 3, 4, 5, 6, those are our 2 middle values, 7, 8, 9, 10. So again, we're just reorganizing the data in ascending order, smallest number to largest number. We then discern the size of the series, 10. And in the case of 10, we have a tie amongst our 2 middle values, amongst our midpoints. So this is really simple. We just add those values together. 5 plus 6, our 2 middle values, is 11. And then we divide that sum by 2. So 5 plus 6 is 11. 11 divided by 2 is 5.5. So our median for this series is 5.5. Easy as that. Go ahead and try this at home. Okay, mode. Mode is maybe the most simple of these particular concepts which we've covered thus far. But in some ways it can be tricky, and we'll get into that momentarily. So the mode is the number which appears most often in a data set. So if you have to do this by hand, it's easy to organize the series in ascending order first. So we've got our numbers all over the place in this series. We're going to reorganize the series in ascending order. And then we have to find which value occurs most frequently within the data series. So as you can see, it's rather evident in this instance that 7 is that value. There's more delicate ways of handling this if it's not so incredibly evident with stem and leaf plots. But for the sake of these examples that we're doing here, since we're just trying to learn this conceptually, I'm not going to get into that in this lecture batch, maybe in a lecture in the future. But as it relates to calculating the mode, always, if you're doing it just in a simplified way, organize the series in ascending order. But in this case, we have a dilemma. We have a tie amongst the values which are occurring most frequently. 2 and 3. So how do we solve this particular problem which we've encountered? Well, if there's a tie between frequency values, it would be bimodal. If there's a two-way tie, 2 and 3, and trimodal if there's a three-way tie. So in this case, there's a two-way tie, 2 and 3, both occur 3 times, 1, 2, 3, 1, 2, 3. And as you can see, 4 appears once, 7 appears twice, 8 appears once. So what we have here is a example of bimodal a bimodal value. So we would answer, if someone asked us to find the mode, we'd have to say data is bimodal because it possesses modal values of 2 and 3. If we had a three-way tie, if we had 2, 2, 2, 3, 3, 3, 4, 4, 4, and then 7, 7, and an 8, well, that would mean that there would be 3 observations of 2, 3 observations of 3, and again, pretend that there's 3 fours here. 3 observations of 4, well, then we would answer data is trimodal, as it possesses modal values of 2, 3, and 4. So don't get confused. If someone says calculate the mode and there's a tie, there could be an instance in which the data is bimodal or trimodal. Don't freeze up, okay? Just follow these steps and you're good to go. All right, standard deviation. This becomes more important as we get into later videos, normal distribution, etc. But in any case, as it relates to just the essentials, the standard deviation is a measure of the amount of variation of a random variable expected about its mean. A low standard deviation indicates that the values tend to be close to the mean, also called the expected value of the set, while a high standard deviation indicates that the values are spread out over a wider range. We'll do an example shortly. As far as variance is concerned, variance is the expected value of the squared deviation from the mean of a random variable. So in most cases, just remember variance as the standard deviation. Just remember the standard deviation is obtained as the square root of the variance. So when you're calculating a standard deviation by hand, which hopefully none of you watching this will ever have to do, one of the byproducts that you get as you calculate the standard deviation is the variance. And the variance is the standard deviation which is obtained from the square root of the variance. And I'll show you what this looks like in the next slide. Variance is often used interchangeably as it pertains to standard deviation. Like someone will say, well, there's a lot of variance in this set. Don't make that mistake. All right, variance when it's being used in a non-colloquial setting and even when you're using it amongst laymen, you should really get in the habit of referring to variance as it relates to this concept, which we're about to discuss, not just throwing around variance as it pertains to a reference to standard deviation, but mistermed. So let's talk about standard deviation by deriving the standard deviation from this sample data set. So we have a sample series. Now, if we were to do this all by hand, a computer will do it for you, and we'll talk about how R Commander and R can handle performing this calculation for you. But just so you understand fundamentally, perhaps how this concept functions, we're going to do this one the long way. So if we wanted to find the standard deviation of this sample data set, we would first have to find the mean. All right, so the mean of this sample series is 5.8. Next, we would subtract the mean from each value within the set, squaring the difference and adding that value to the next subsequent set value. And what that would look like is the mathematics that I have below step 2. We would then have to find the variance of the set value by dividing the value derived from step 2, so that would be 61.6, by the total number of set entries minus 1. So there are 10 observations. So we would take this value here, 61.6, and we would divide it by 9 because there were 10 observations minus 1. So 61.6 divided by 9 is 61.6 divided by 9 is 6.84. So 6.84 is the variance. We now need to find the standard deviation. So the square root of the variance is the standard deviation. So the square root of 6.84 gives us the value of 2.62. So 2.62 is our standard deviation. And if we were to square 2.62, we would get the variance, which is 6.84. So the variance is probably most important from a pragmatic standpoint as being remembered as a byproduct of this equation, which is utilized to derive the standard deviation. Because without the variance, as we go through these steps, we wouldn't be able to derive the standard deviation. All right? So we go through all these steps, we get the variance, which is 6.84. We take the square root of 6.84, and we have the standard deviation. So the standard deviation is 2.62. So we would maybe could go through this particular standard deviation exercise, but I feel like it's a little premature for that, so we won't do it in this batch of slides. However, I do want to demonstrate what we were discussing as it relates to where values would be, assuming that a observation series is sampled from a normal distribution. So if we were sampling data and we have our sample set, which is 31 to the value of 3 there, and we were to derive the mean is 21, which is here, and the standard deviation is 19.27. So as you can see in this instance, the values are not clustered about the mean. They're over here, but our mean is here. In this instance, however, we have a mean of 10.5 and the standard deviation is 5.89. So the values are on the number line are found closer to the mean value. Now, this is a bit confusing as far as examples are concerned because unless these we're measuring two comparable phenomenon, and in that instance, it would be apples to apples. We can't really state that data is, our data observations are closer to the mean in one instance versus the other as it relates to the measurement of the mean and standard deviation. And we'll get into what that means as we start to look at the lectures and videos related to normal distribution. But just know that if we're sampling similar phenomenon and we're looking at mean and standard deviation values, what we're looking at really is variability. So just as a quick example, I suppose, off the top of my head, if we're looking at, say, quarterbacks, right? Quarterbacks who are currently playing in the National Football League, and we'll say that these are two different quarterbacks on two different teams, and they're playing in the same season. And each has a similar mean. So we'll say the means are similar. We'll say that each mean is about 21. But one quarterback has a higher standard deviation as we're looking for, say, points scored via touchdowns in a game. We'll say that one has a higher standard deviation than the other. Well, that would mean that this particular quarterback, what you would expect for them as you would be sampling the data, you'd expect there to be a larger amount of variability in their performance game to game, week to week, than there would be from a quarterback who has a similar mean but a lower standard deviation. So a way to think just in layman's terms of standard deviation and mean is an average, and standard deviation is sort of an underlying volatility as it relates to what you'd expect when comparing phenomenons or comparing, I guess, yeah, comparing observational series from a similar phenomenon. And we'll get, again, more into this as we talk about the normal distribution. So if you made it this far, I appreciate it. I appreciate you tuning in and sitting through this rather long lecture. And if you were able to take away anything from this particular lecture, please consider liking and subscribing. It would mean a lot. And I look forward to seeing you again. Best of luck on your research and your understanding of these concepts, and I hope to see you again soon. Take care.